Good morning. Let us see today what is black body. What is black body? What are black body radiation curves? How are these black body radiation curves are obtained? What are the deficiencies of classical mechanics? What are the drawbacks of classical mechanics? The classical mechanics failed to explain the black body radiation curves, whereas quantum theory is able to explain the black body radiation curves. Okay. Now let us see what is a black body. Any object that absorbs all the radiations falling on it is called a black body. What is a black body? Any object, any body that absorbs all the radiations falling on it is called a black body. Now, a perfect absorber is also a perfect emitter of radiation. A perfect absorber is also a perfect emitter of radiation. For example, on heating any object, okay, it emits lights of not a single wavelength, it emits lights of different wavelengths. For example, an object is heated at temperature T1, the curve is obtained. It emits the body, the black body emits all the wavelengths, but there is lambda max. That is, for example, on heating, there is a distribution of energy. See, there is a distribution of molecular velocity. Similar to that, there is a distribution of energies emitted, it is radiated. Okay, so on heating, for example, iron rod, let us take iron rod, you heat it in the flame, okay, for example, at 800 Kelvin, at 800 it becomes red hot, emitting red light, largely red light, and also it emits other wavelengths. For example, lambda max is red light, T1. Okay. Now, at further high temperature, on increasing the temperature, for example, T2, that is 1500 Kelvin, the black body emits all the different wavelengths, but the lambda max shifted towards left, that is the wavelength is decreasing, that is blue light, emits blue light, that is called blue shift you are studying. Now, the energy density, the next point is the energy density. The amount energy density is represented by E nu, d nu, is the amount of energy radiated, depends upon the temperature. See, at low temperature, the amount of energy, the area under the curve is very low. At high temperature, the area under the curve is, the amount of energy emitted is high. Now, what happens when the object is heated? When the object is heated, they absorb the energy, the body absorb the energy, and the electrons jump from lower level to higher level, and when the electrons come back to ground state or first excited state, they emit radiation. That is called black body radiation. Okay. Now, the black body radiation curves I have shown here, okay, gives the correlation between the energy density versus lambda or frequency of the light emitted at different temperatures. Okay. Now, for example, at temperature T3, this is the curve, this is the black body radiation curve obtained for high temperature, and this is for low temperature. Now, at higher temperature, as you see, at higher temperature, the position of the lambda max, for example, at temperature T1, it emits largely red light, lambda max, that is lambda max. What are the characteristics? For each temperature, there is a particular lambda max, at which the energy radiated is maximum. For example, at T1, lambda 1 max. T2, this is the lambda 1 max. Okay. At higher with increasing temperature, the lambda max, the position of lambda max shifted towards the lower temperature. The position of lambda max shifted towards the lower wavelength. Similarly, higher the temperature, the peak or the intensity, the energy density is maximum energy high. That is, the peak is more pronounced with the increasing temperature. Now let us describe the curve. For example, as you see, lambda max is inversely proportional to temperature. Lambda max is decreasing with the increase in temperature. Lambda max is decreasing. Therefore, lambda max is inversely proportional to temperature. Lambda max T equal to V, where V is called the proportionality constant. This relation was obtained by Wien, called Wien displacement law. He was awarded Nobel Prize for this, for describing the black body radiation curves, experimental curves. Okay, using classical mechanics, the energy levels are continuous. And realizing law, the following the calculated the obtained curve is shown here for using classical expression. This curve, the dotted line curve, is obtained. Okay. Therefore, the classical theory is inadequate to explain the black body radiation curves. It is not able to explain the black body radiation curves. This is because, for example, in classical theory, the energy levels are continuous. See, as you increase the temperature, the lambda, it will increase, the energy, it will increase and increase. Okay. So, whereas in quantum theory, the energy levels are quantized. The electrons are bound in an atom. It cannot go to very, very higher level. Okay, it can go to higher level, but not okay. So these black body radiation curves was explained using quantum theory. The black body radiation curves was explained by using quantum theory. Max Planck proposed quantum theory. He used quantum theory and derived the energy density versus frequency. This is the energy density versus frequency curve. This will be opposite. Okay, this will be lambda max with the increasing temperature. Lambda max will be decreasing. Here, with increasing temperature, see, red light, blue light has greater frequency than red light. Therefore, lambda max will increase this way. Okay. Now, as I said earlier, using quantum theory, Max Planck derived the relation, and this relation is successfully used to explain the black body radiation curves. Okay. This expression, Max Planck expression, can be used to describe the black body radiation curves. E, that is 8 pi h nu square. Here h is not there because Planck constant. This is h nu. E is equal to h nu. The energies are, when the body is heated, the energies are emitted in discrete packets called quanta. E is equal to, that is h nu. The energy of the quantum of light is equal to E is equal to h nu, where h is Planck's constant, nu is the frequency of the light emitted. Okay. Therefore, this h is here there is no h, and the nu q d nu e c cube e power the c is the velocity of light, e power h nu by kt minus 1, where he has introduced the quantum concept. The energies are emitted in quanta. The energies are emitted in quanta in discrete packets called quanta. So minus 1. Using this expression, the curve could be explained. The black body radiation curves could be explained. Therefore, it shows, the black body radiation curve shows the inadequacy of classical mechanics, inadequacy of classical theory. Okay. So he was awarded Nobel Prize for propounding quantum theory of radiation and also derived this relation, this E is equal to the famous E is equal to h nu equation to describe the black body radiation curves. Thank you for watching.